everybody. Very good morning, everyone. So we have a wonderful speaker from Texas A&M. Because I got my PhD from Texas A&M, so I'll say howdy to everyone. That's how we greet everyone. We have Professor Srikanth Saripalli from Texas A&M in the Mechanical Engineering Department, and he's the director for Center for Autonomous Vehicles and Sensor System. It's called the Canvas at Texas A&M University. He holds the J. Mike Walker 66 professorship. His research focuses on robotic systems, particularly in air and ground vehicles, and necessary foundations in perception, planning, and control systems integration. He is currently leading several efforts in off-road autonomous ground vehicles. He has also led several long-term, more than 6-month on-road deployments of autonomous 18-wheeler trucks and slow-moving shuttles in Texas. He is currently interested in developing and deploying autonomous shuttles on campus and in cities. He's also interested in developing such autonomous shuttles for mobility challenge and paratransit applications. Thank you so much, Srikanth, for finding time. Please enthrall us, impress us with your talk. Thank you so much.
Thank you. Thanks a lot. Hello, everyone. Since I thought I would say howdy, but there enough howdy. So my name is Srikanth Saripalli. I'm a professor in mechanical engineering. And today I'd be talking about probably a decade's worth of work that we have done in autonomous vehicles. And the talk is titled as Autonomous Vehicles in the Wild, which is the kind of things that you encounter when you have autonomous vehicles that are actually working in real life, right? So I'm hoping that the talk would be interactive. So if you have any kind of questions, if you have any kind of thoughts, please stop me. I'm trying to figure out how I can see the chat window here and the participants. Okay, I can see them. The talk's primarily about air and ground vehicles and kind of discusses what we've done in the last 10 years with our deployments of real vehicles in real world, and what are the lessons learned, and where should we go. And I think the talk is while I didn't plan for it, if you have read the news in the last 1 week, GM, Cruise, all their autonomous vehicles have been pulled away from the streets of San Francisco, and Cruise has voluntarily recalled all of its 950 vehicles from pretty much all over US because of the accident that happened in San Francisco, right? So I think we are still ways away from true autonomous vehicles. And so that's really what I'm going to talk about. So I'm going to make this full screen, and hopefully everybody can see this in full screen. If you can't, please let me know. Okay, I'm hoping everybody can see it in full screen. A little bit of history, right? So when we start talking about autonomous vehicles, everybody kind of says, well, why aren't we doing this? So there are two camps. There's a camp that kind of believes, probably a lot of startups that believes that autonomous vehicles, you can just make an autonomous vehicle without any kind of infrastructure or rules or regulations, and that would work, right? So these are probably all the startups that are there. To the camp of people, so well, maybe there are three camps. One camp that actually doesn't believe that we will ever have autonomous vehicles. And then probably there's a third camp that kind of believes that, for autonomous vehicles to truly work, you need some legal and some regulatory framework before autonomous vehicles can be used, right? So I just wanted to kind of give you a little bit of perspective about automobiles, right? So in UK, in Britain during 19th century, when the first vehicles were introduced, automobiles were introduced, the speed of those automobiles was manually set to 4 miles per hour. And the requirement was that a person would run in front of the vehicle, right, with a flag telling everybody that, hey, there are vehicles that are coming, please step away from these vehicles, right? So there was an actual act, and this is called the Red Flag Act, right? So this kind of gives you a perspective. So if you close your eyes and kind of think about, well, the vehicle now is one of the Waymos or the GM Cruise vehicles or something like that, there's still a remote operator. There are kind of still people who kind of figure out what happens when these vehicles have to interact with emergency vehicles and things like that, right? But more importantly, if you go to 1925, so the picture on the right is actually New York in 1925. And if you see that, populations over 25,000, 2/3 of the deaths that were happening because of automobiles. And this was basically the headline on New York Times. And this was because at that time, roads were kind of places where people walked, right? And so there was a big lobbying by the auto manufacturers, Ford at that time, kind of making sure that roads are not safe for people. And so we kind of went from a person could pretty much walk anywhere on the road to no, roads are really for automobiles and people should only walk on sidewalks, right? So that required a big shift in the regulatory framework to get to that, right? And I think we are exactly at that same moment, right? So people are realizing that, the idea that autonomous vehicles are going to be these magical things that are going to do everything is probably not going to work. But autonomous vehicles are still very, very, very useful, but they require some regulatory help before they are going to kind of get over and actually be used everywhere, right? So this kind of puts it in perspective. And this is a video, I won't play the entire video from 1957. This is a video by GM. Hopefully. So I'll stop it there, but you could kind of say that when people kind of start thinking about, well, integrating infrastructure with autonomous vehicles is a new idea. Well, people have been thinking about it from the early 1950s. This is an ad that GM came up with where they were trying to sell their car. So folks have been talking about a lot of these things, right? So some of them are not feasible because of the amount of money that is involved in it. Some of them are not feasible because there was never a regulatory push to get them working. And some of them were just bad ideas. And so they were not feasible, right? So this kind of gives you so I see something in chat. Okay, so I can't, if you have questions, just please ask the question because I'm trying to monitor the chat, but maybe I'll miss that. So now from autonomous vehicles, when we think about automobiles, I want to kind of shift to UAVs also, right? So, and this is one of my favorite stories about all of autonomy, right? So the story goes like in 1849, right? The Austrian government, the Austrian king wanted to invade Venice. And so what he does is basically he brings up all his science ministers, everybody, and kind of asks the question, well, how am I going to invade Venice? I want to have minimal loss of life. So how do I do this, right? So the science ministers, they come in and they kind of say, you know what, how about we create these balloons and each of these balloons actually has some explosives on them. We fly these balloons, and at the perfect time, we pull a cord, and the cord basically carpet bombs all of Venice, right? So they actually end up doing this, right? So they build these 200 pilotless balloons, and they fly these balloons over the city of Venice. And at the appointed time, they pull the cord, right? But they forget one big thing. So, because I can't see many of you, so I'm just going to tell the story. So they forget about wind, right? So the balloons, instead of, sorry? So the balloons, instead of actually going on Venice and then carpet bombing Venice, they basically, because of wind, they fly towards Austria, and then they bomb Austria, right? So when we work on a so was there a question?
No, we're just laughing at it.
Okay. So this is and the reason this is my favorite story is that it tells us a couple of things, right? So if you want to do robotics or autonomy in the real world, you always want to think about environmental constraints, right? You cannot say, well, it's going to be perfectly nice. There are not going to be people walking anywhere. There are not going to be things that are happening. I know everything about everything that's happening, and now I'm going to design a system that works. That will never really work in practice. Okay. The other thing I believe, and I might be wrong, is I think this is the first use of remote controlled flying objects to do something useful or bad, right? However you want to put it, right? I haven't been able to find something before this, right? So there are definitely after this, the term drones comes from the British aircraft, where they used to use them in World War I for actually testing how good the pilots were, but that is much later. That's in the 1920s and the 1930s, right? So this kind of gives you an idea, right? So if you want to work in autonomy, you have to think about the environment. You have to think about the known unknowns and the unknown unknowns before you start working on these things. Okay, so that kind of gives you a broad kind of, let's say, history lesson, right? So broadly, if you want to work on autonomous vehicles, you need some regulatory help, right? And when you work on autonomous vehicles, better be thinking about the environment, the known unknowns, the unknown unknowns when you want to really deploy them, right? And the rest of the talk is really kind of how we have done it. What are the things that we thought we knew, and what are the things that we had no idea would happen, and the things where we spent a lot of time trying to figure things out are things that actually did not matter in real life, and and we learned quite a bit, right? So that's kind of the rest of the talk about what I'm going to talk about, right? So before we get started, I just kind of want to give you when I talk about autonomous vehicles, where actually are we situated in autonomy, right? So there's the Society of Automobile Engineers that has come up with these 5 levels of autonomy. Everybody of us kind of agrees that these levels are kind of bad. They don't make sense right now. So let's not worry about it, but everybody kind of uses these levels, right? Because everybody knows them. So think about it. Level 0 is no automation at all. Right now, you cannot buy a car that has no automation. Absolutely not anywhere in the world, right? Level 1 is drive assistance, right? So cruise control, park assist, things like that, right? So the way to think about it is you probably can give steering and to something, so that's or brake and throttle, right? So that's cruise control, but not everything, right? So this is where most of the American cars are. So Ford, GM, when you buy something, this is kind of what you would get, right? You would get minimal cruise control. You'd probably not get park assist, right? Level 2 is partial automation. So kind of think about adaptive cruise control and lane keep assist. Pretty much any of the Japanese, Korean cars that you buy are actually level 2, right? So there's a lot more focus on safety. So a standard off-the-shelf Hyundai, Toyota, Honda, Kia are basically level 2. Even Tesla, irrespective of what Tesla says, is a level 2 car, right? And then level 3 is, the way to think about it is hands off, eyes off sometimes, but your mind is still engaged, right? Level 3 is basically lane changing, pedestrian avoidance, things like that. So this is where you can think of like Ford's Blue Cruise system sitting, or the new Mercedes level 3 system that they've recently introduced in Germany, and they plan on introducing it in Vegas and out in Nevada, at least, is a level 3 system, right? So almost all autonomous companies want to go to level 4, right? Which is high automation. So the idea is that you can't get autonomy to work pretty much everywhere or anywhere in the world. That just doesn't make sense. But you want autonomy to work where you actually can make it work, right? Where there's a business case if you're a company, or where it makes sense to actually have it working, right? And the way to think about it is your hands can be off, your eyes could be off, so you could be sleeping, but your mind and mind off sometimes, right? So not all the time. That's kind of, there are lots of issues with that. So there are lots of physiological and psychological issues, like if you have to take over and if you're sleeping in the back of the car, and you're all completely groggy, how are you going to take over, right? So the car needs to kind of pull over and come to a safe point before you take over, right? And level 5 is full automation. I don't think anybody wants to do level 5 because we all kind of understand that you can't do this everywhere and anywhere that you want to do it, right? At least not right now. So this kind of gives you a structure to kind of talk about, and this is, while this is primarily for automobiles, people kind of, you can think of the same thing for UAVs or things like that, right? So now coming back to what I do, right? So that kind of gives you a kind of like a history lesson where kind of talk about how automobiles started, what UAVs happened, things like that. So what do we do out at A&M, in my lab and in our center? So our focus is on developing perception, planning, control algorithms, but the main focus is to actually integrate them in the real world, right? So at the right, the picture that you see is an autonomous shuttle that we ran for 6 months out in downtown Bryan, right? So College Station Bryan is where Texas A&M is. So we actually gave rides to the community for 6 months, and we kind of asked questions about what do we understand. So this was a free thing that we did for 6 months. We ran from morning 10 o'clock to 12 o'clock. We gave rides, fixed ride, drop off, drop on schedule for everybody to kind of understand how viable are these shuttles, right? And then on the top left, you see an 18-wheeler truck. So we work quite a bit with a lot of companies that are currently working in the state of Texas for automated trucking, right? So the goal is to help them in perception, planning, and control as to how you do that, right? So I'll kind of talk about some of the issues. And then in the center, you see a lot of work that we are doing for Army Research Labs and the Department of Defense, where we are looking at off-road autonomy, right? So the question there, of course, is you're in a GPS denied state, and then you want to figure out how you get to a particular point and how you go there, right? So before we get there, I want to kind of differentiate between the center vehicles, if you want to call them, so the 3 vehicles that you see, and the top left and the right side vehicles, right? So one is on-road autonomy and one is off-road autonomy, right? So what's the difference, right? So the big difference, if you think about it, is in on-road autonomy, there is a road. So you kind of know that you have to drive on the road, and anything that you see on the road that's in front of you is an obstacle that needs to be avoided, okay? Whether that's a person, whether that's a trash can, whether that's something else that's on the road, you kind of want to follow the rules of the road while avoiding things, right? So the complication that comes in on-road autonomy is really from the behavior of other people and other cars and how to do that, right? So that's the main complication. In off-road autonomy, you don't have a road. True off-road autonomy is So think about the bottom center picture, right? So you can go through grass. You don't want to hit a tree, okay? So the biggest question is, where is the load-bearing surface? How do I know that this particular surface is okay to drive on, right? When beneath that grass, it could be a muddy soil, it could be quicksand and things like that. And how do I know what are things that I should be avoiding versus what are things that I can just plow through, right? So that's a different kind of question that you're answering, of course. And of course, you don't have GPS. So you're kind of stuck with, I want to do all of this on my own, on the own vehicle that I have, right? So that's the big question. So let me talk a little bit about our shuttles. So we ran the shuttles for about 6 months. And then we were going to do a next phase where we were going to run these on A&M campus and also run them on other campuses. But of course, that's when COVID hit. So we kind of shut down the entire thing. So you could see one of the pictures. This is, of course, the chancellor of A&M. And then we had the mayor here driving those shuttles, right? So we had deployments at downtown Bryan. And the question mainly we get asked is, why did you do this? And how is this different than, say, Waymo doing these or things like that, right? So our main goal is to look at pedestrian-rich, slow-moving environments, right? Campuses, hotels, downtown communities, things like that, right? And they're relatively structured environments, and you're going fairly slow, so the cost of doing something bad is lesser than other things, than if you're going relatively fast, right? And we, at that time, so this was 2018, this was an area that was less explored, which is there were a lot of people looking at highways, freeways, autonomous vehicles, but not many people looking at these like close things, right? The other advantage is you could actually use infrastructure. So if you realize that there is a particular area in, say, downtown Bryan where it's very hard to drive the shuttle because, let's say, you're not getting GPS data, or let's say it's just that it's too crowded, things like that, then you can actually get it in aid from your infrastructure, right? So you could put a fixed camera there and then figure out what's happening, and you can. So it makes the problem less easy. So instead of just saying we want to do everything on the vehicle, you can do some things in the infrastructure, some things on the vehicle, and you can aid this, right? But the main goal for this was to ask the question: could we aid in paratransit applications, right? So at least I believe on most university campuses, paratransit is a big deal because there's not enough funding for it. And of course, you need to actually take people from one place to the other place when they need to go. And of course, they cannot go, right? So that's why it's paratransit. So could we have these shuttles with an app so that you could actually have these, were able to take these people, right? So this kind of shows a video of this running in real time. And you can see that we're fairly successful. We've taken kids, we've taken, and this is a fixed drop-off, fixed set of routes. So it's not like you can go anywhere. This is downtown Bryan, and this was kind of with actual traffic over there. But the thing that we realized after we ran this was that because these vehicles are so predictable, the general population becomes very, very comfortable while these vehicles are running. So after the first week of running these vehicles, we would have people actually crossing us both from the left side and the right side, right? So they were constantly ignoring the rules of the road because they were like, well, this vehicle is always going to stop, you know? And we would have people just, pedestrians just crossing even when the vehicle has the right of the way and is going, right? So, and that's a big issue, right? So if the pedestrians know that this vehicle is always going to stop for pedestrians, you know, they're not going to follow the rules of the road, right? And we saw this even at four-way intersections, which is because all the rest of the cars knew that this was an autonomous car and it would always follow the rules of the road. The other cars would even go first, but before, even though we had the right of the way, right? And so if you had passengers in your car, those passengers would actually get very annoyed because they would not be able to go, right? So that was the big issue. We had not thought about it. Of course, now it kind of says, aha, that makes sense. But we had not thought about it. You would assume that people follow rules and things like that, right? But as it turns out, once they realize that this is an autonomous vehicle, it always goes very slow. It follows the rules of the road. So I'm just going to cut around it in any way possible and just go do my work, right? So that was a big issue. And we didn't have any good answers for that, right? So that I think is still an unsolved issue as to what you do with it, right? So I'm going to kind of jump from, so we did these shuttles, and that was one of the big takeaways for us, is that once you deploy these shuttles, and once the population kind of gets used to these shuttles, you have to kind of work more on the aspects, the community aspects of how they kind of work along with it, rather than actually the technological aspects of how you run these or what these algorithms are, things like that, right? And then the second part of it, really, in this was, so there were lots of places. So like over at this place, right? So if you see this, there are lots of cars that are parked here. Oops. And these cars, of course, they're all parked. So normally, if you have a vehicle that is coming, these cars would wait for this vehicle to pass before they would get out of this parking spot. And that was not the case. Once they realized that this is an autonomous vehicle, it has sensors, and with the sensors, it would stop, these folks started getting very aggressive, right? So we had this kind of like tension between, well, what should we do? Should we follow the rules of the road, and can we only do the things that are actually possible, or should we become more aggressive, right? Like a normal driver to get these things done, right? And this is, I think, the biggest factor that is stopping autonomous vehicles, right? So if you know that an autonomous vehicle is always going to follow the rules, you can pretty much do anything that you want, right? So something that we learned, something for which we don't have an answer, right? So now I'm going to kind of go to the next part, which is the off-road part. So we've been working with Army Research Labs on a project called DARES, and this is really distributed virtual proving grounds, right? And let me kind of actually. And the idea here is that we are always short on the number of real vehicles that we need for testing, right? So for example, if I have 5 vehicles and UT San Antonio has 10 vehicles, but we needed to test with 100 vehicles, there's no good way to do that test because we really don't have 100 vehicles to do this, right? And so what we said was, hey, would it be possible to create these distributed virtual real proving grounds for evaluating autonomy that is relevant to the Army, where you have some real vehicles that are being tested, say, at A&M, but some vehicles that are being tested by the Army in their own test facility. And then we have virtual vehicles that can be operated in either facility, and these could all be tested at the same time, right? And so we've been working on this project. This is a cooperative agreement. And so the biggest question then becomes, how do you represent these environments? And is there enough data for actually working on these off-road environments, right? So one of the big takeaways when we started doing this is, as it turns out, a lot of these machine learning algorithms, particularly in perception, are not generalizable to off-road vehicles. And let me actually skip. I'll come back to this. But so this is a kind of like, this is a little bit old. So this is about 2019, but kind of gives you a table. The top table kind of tells you all the data sets for urban environments. And there's a lot of data sets for urban environments. Now in 3 board years, you have a lot more data sets, right? But there are very few data sets for off-road environments. So one of the first questions that we asked is, can you train an algorithm on any of the urban data sets, and how well does it work in an off-road data set that the Army is interested in, right? Now, if you think about it, it's not just the Army, it's anything to do with agriculture, construction, mining, pretty much any place where you don't have infrastructure, where things are going. As it turns out, your current state of the art, or at least even now, I believe, most of the algorithms actually fail miserably when you want them to kind of figure out what they're looking at, right? So, so what we did, the first part that we did, so if you take an environment like this, right, and you kind of ask a very simple question, can you segment it out to tell me where grass is, where water is, where there's a tree, where there are probably these obstacles in it, where mud is, things like that. The current state of the algorithms fail very badly. So we first developed a data set, we call it RELIS 3D. This was 2019. Now, as far as I know, this is one of the most widely used data sets for off-road environments. So what you see here are, the top is the raw images and the pictures. The center is the images annotated. So we painstakingly annotated a lot of these images. And then the bottom is the point cloud data that is also painstakingly annotated, right? And it basically all it says is that we probably have one of the most comprehensive data sets when you're looking for off-road environments. And it actually, when we compared it, at least this was, again, 2019, so some of these numbers are probably not relevant right now, but for something like Cityscape, if you use one of, at that time, at least one of the traditional state-of-the-art perception algorithms, you could get a very high mean IOU out of it, about 80% in terms of perception. But if you ran it on, say, an off-road data set, you get very low, about 40, 50%, right? And that's because the image label distribution is very skewed, right? So you mostly see sky and grass, but if you're interested in things like barriers or logs or fences, these are fairly small objects. So unless you train on them, you won't be able to see them. And this is actually true, even worse for something like point cloud data. So if you're trying to do this in like point cloud LiDAR data, the current state-of-the-art algorithms work very well in very structured city-like environments, but they work very badly in like unstructured environments, right? So it kind of, let me run this so that you have it, and kind of, so this is the kind of terrain that you're looking at, which is very relevant for, say, the Department of Homeland Security, Army, things like that. And as it turns out, there's not enough data there to train your algorithms when you do this, right? So this was another kind of the thing that we expected as we were trying to do this, that perception would be fairly simple given the state of the art in machine learning and deep learning techniques. And now with vision language models, we expect that these would be good. We've started looking at vision language models like Dino and things like that in off-road. And it's the same state. While they work very, very well in structured environments, they don't work as well in unstructured off-road environments, right? So, so that was, now going back, so that was the first thing. And then the next thing, of course, is when you're trying to solve these problems in off-road, right? So this is, here you have a vehicle that's autonomously following a path. It doesn't have GPS. And it's been told to go to the other end of that gorge. And as it goes down, it sees this nice flat ground, and it says, okay, I'm going to go through that ground. But as it turns out, that's quicksand, right? So it gets stuck there, right? So and these are the kind of things that you don't see in on-road situations, but this is quite normal in off-road situations, right? Or if you look at this, so this is a 4-wheel drive vehicle, but of course, while it's climbing up this thing, it actually can be tilted. So we had to take over because it was going to get going to fall back. And then the final thing is you have negative obstacles. And negative obstacles are really, really hard to determine, right? So the equivalent of negative obstacles in on-road is potholes. So think about a pothole that's filled with water or it's filled with mud, and you have to make a decision whether you're going to go around that pothole or go through that pothole, right? Now, potholes are really small, so probably okay. But in off-road situations, you have these negative obstacles. So, and you have to kind of figure out where those negative obstacles are before you can kind of avoid them, right? So these are situations that you normally don't see on road. And so these are still kind of open problems that you want to solve in autonomous vehicles, particularly in the off-road domain, right? So now coming back, so this was actually about off-road domain, but then coming back to the question of how do you do these distributed virtual real proving grounds, right? So here's a video of how we can do this. So on the top left, you have a real vehicle running inside the lab, right? And the bottom left kind of shows that same thing running in a virtual environment, interacting with two virtual vehicles, right? And it's being controlled by somebody sitting somewhere else, right? So we can take something that's running in a real world, put it in a completely virtual environment, running in a virtual world with multiple virtual vehicles, and they could all be interacting together to do this, right? Of course, the big question from the Army then is, well, can you kind of fake the tire terrain interactions so that the vehicle's running in a flat world, but it feels like it's running in a say a bumpy or a grassy kind of situation, right? And so we've been working on that quite closely with Army Research Labs to look at things like tire terrain interaction and terra mechanics, and how we can take those and put them into these models so that we can do that, right? So what does this help us? So you could do a lot of testing in a virtual world while that is interacting with real vehicles that are geographically separated, right? So you could have some vehicles that are working from, say, so the lab that you see here is, this is our lab, but we have worked with Army Research Labs where those folks are actually sitting in Maryland, and they actually have real vehicles running out at Maryland. We have real vehicles running in our lab out at A&M, and all of them are interacting in a virtual world that is a replica of something else, right? So a third world that is, say, this is actually Relis. So it's a facility that we have at Texas A&M for testing that we created a 3D model of where we can do this. Right? So again, the take-home message from this is that, so for on-road vehicles, there are questions about how the behavior of pedestrians, how the behavior of vehicles kind of changes when you have real vehicles running in the environment, and how you want to kind of take that into account when you start thinking about autonomous vehicles, right? In off-road, right now, we are still at the beginning because a lot of the things that work in on-road don't actually work in off-road, right? So that's the first take-home message. The kind of problems that are relevant in off-road are things that we are still at the trying to figure out fundamental questions about perception, right? There's no good way to detect quicksand unless you have a ground penetrating radar. GPRs are still in the $500,000 range, and they're not practical enough where you can put them on, say, small robots and things like that. Negative obstacles are still something that we don't have a good handle on how to do it. And then dynamics and stability are things that we are still trying to grapple, right? So off-road is still kind of open if you want to look at off-road autonomous vehicles and what you want to do with it, right? And then the next, of course, is how do we make sure that we can test this in all kinds of environments, all kinds of weather? And so the idea is to kind of think about this distributed, virtual, real, mixed reality proving ground for testing them. Of course, there are open questions about how do you do tire terrain interaction, right? How do you take care of latency? And then you don't want to be transmitting all of the data over a network and then kind of clog the network. So for example, if I say a chair, I'm sitting in a chair right now, all of you kind of understand a chair. You might not know whether I'm sitting in a four-legged chair, three-legged chair, or I'm sitting in a couch or something like that. But that's immaterial to the conversation that we are having, right? So that's the, can you start these interactions by looking at these symbolic representations and semantic representations together, rather than working on, say, raw point clouds and raw images and things like that, right? So now I think I have probably 10 minutes. So let me kind of change gears and talk about aerial vehicles, right? So I've talked about, so this kind of, for ground vehicles, kind of the take home message is we need better data sets. We need better simulators. Now there's a question of, do you want better simulators or do you want worse simulators? Okay, because maybe the world, like I said, you should always be worried about unknown unknowns in the real world. And so maybe training on worse simulators is actually a better thing, or simpler simulators is a better thing than training on the best simulators, right? And then robustness of machine learning, right? As it turns out, a lot of machine learning algorithms overfit. Overfitting is good, actually, if you know the problem that you're trying to solve, right? But once you go into real environments, you do not know what's there. And so your overfitting usually leads to unexpected scenarios. And I think the current issue that's happening with Cruise is an example of that, right? And then how can we do more human-like testing, right? So, and that's a question where maybe large language models are good because they kind of sometimes give you crazy answers, and crazy answers are good if you want to test real life situations, right? So now I'm going to shift to talk a little bit about, in the last, say, 8 minutes, about aerial vehicles, right? So one of the things that we've worked on for a long time with aerial vehicles is landing, right? So the idea is very simple. You have a helicopter, you want to land it on a ship deck. And the reason you want to do this is currently the way this is done is you have a helicopter, and if it wants to land on a ship deck, and if the sea is very rough, the helicopter pilot actually drops a anchor, and that anchor is rigidly associated with the ship deck. So if the ship deck moves like this, the helicopter moves like this, right? And so then the helicopter pilot only has to worry about the height control and not worry about attitude and pitch control. So of course, this is in very high rough seas, right? So this is an open problem for the Navy, when particularly the Coast Guard, when they want to actually go do rescues in very, very high rough seas, right? Oops. So this is there have been quite a number of works and landing on targets, and this is one of our works on landing on moving targets. So the reason I want to show this is to again kind of go back to the question of, so we worked quite a bit on aerial vehicles, both helicopters, fixed wing vehicles. And the reason to kind of think about this is that, again, this is a problem that you can look at this video and you can do one of two things. You can say, wow, this video is cool. You're actually landing on a moving vehicle that has actually attitude motion, right? Roll and pitch, which is true. You can also look at this video and kind of think about the 100 ways this experiment will fail, right? Which is true. What if there was like a bump here, right? What if the vehicle suddenly decided to veer off and go in this particular direction? How would the helicopter, just before this helicopter was touching, what if the vehicle suddenly decided to accelerate, right? So there are hundreds of ways of kind of making this system work or making this system not work, right? And that's one of the take-home messages that I wanted to show from this, was really that in field robotics, when you test autonomous vehicles, whether they're air or ground, testing hundreds and thousands of times actually matters, right? So because a lot of times you do not know the kind of things that you have missed unless you start testing. Okay, here the question, of course, is you want to test for all the parameters that would happen on a ship deck, but you don't want to test for the parameters that wouldn't. So the generalization of this is probably not very useful, right? Landing on a moving target that is both pitching and rolling in the general case is not something that you want to solve, because there are other ways to kind of simplify the problem. Okay, but that is true if you're only working on a solution for a Coast Guard where they actually need this, right? So similar thing. So we worked quite a bit on aerial vehicles for obstacle avoidance, and this was one of the DARPA programs where we had to detect a 6 millimeter wire here at very high speed. So this is flying at about 10 meters per second. This is work with Carnegie Mellon and avoid that, right? So you see this 6 millimeter bar, but of course represented as 1 meter blocks on this. And so it has to kind of find that and avoid this, right? So we did enough tests with this. So we probably did about hundreds of tests with this for DARPA. But the big thing that we realized here was that if you, let me play this. Okay, stop it here. So the problem is that perception systems are very, very finicky. And so if you fine tune your LiDAR a lot, as it turns out, your LiDAR starts seeing dust. And then the helicopter, because if you see enough dust, the helicopter starts thinking about this as obstacles and then starts avoiding imaginary dust particles as obstacles. And if you don't fine tune your LiDAR, so depending on the environmental conditions, sometimes you miss seeing this 6 millimeter wire, right? So the requirement was you have to see a 6 millimeter wire and you have to avoid that at speeds above 10 meters per second, right? So, I mean, this was a successful program. We were able to kind of show that over multiple runs on multiple days. But that required a lot of fine tuning of perception, particularly the LiDAR gains, to make sure that you would not see dust. And it's an interesting question when it comes to how perception interacts with planning or control, right? So if you see, you can easily say, well, if I see one dust particle, you know what, that's something I'm not going to worry about it, so I'm not going to avoid it. What if you see 10 dust particles? What if you see 100 dust particles, right? Are you going to just kind of think of them as, oh, I'm just going to ignore them and kind of not worry about them, right? So that's a question that kind of goes from your low-level perception, planning, control to maybe a high-level situational awareness of what exactly are you trying to do? Where are you, right? So, and how, would you kind of, what does that mean, right? So for a human, these questions are fairly easy. For a autonomous vehicle, these questions go to the heart of how you design your autonomy algorithms and how you kind of solve those autonomy algorithms, right? So I'm at 11:48, so I'm not going to talk about these parts, right? But I'm going to skip to the last slide, which kind of talks about the lessons learned, right? So the title of the talk was Autonomous Vehicles in the Wild. And what that means is that how do you get these autonomous vehicles to work in real life situations, right? And the second part of the title was the good, bad, and ugly, right? So the good thing is that we definitely can build autonomous systems that work in limited environments. If we know the environment where we are going to work, and we have a good sense of the environment, autonomous vehicles right now can do the task, right? So if you think of Google's, the Waymos and the Cruisers, the first thing they do is they go and map the entire environment. And they keep on doing this. It's not just they do it once, they do it every week and actually sometimes every hour, right? And that's the first part, right? So if you know what's happening in the environment, we can do this, right? The bad part of it is you need to spend a lot of time tweaking your systems. Generalizable autonomy is a long way off, right? So here are some of the things that you want to do, right? Calibration is very, very, very important, right? People don't talk about it. It's one of those things in robotics where everybody kind of understands how important that is, but we just don't talk about it, right? Sensors, there's people kind of fight about it. Should we just use vision? Vision kind of works. Should we use LiDAR? LiDAR kind of works. Should we use radar? Radar kind of not works. Simple answer is right now, till we get to a point where we actually know what generalizable autonomy is, you want to use as many sensors as it works, right? Because vision is great until it fails. Simple example, you go into a parking garage, you come out of a parking garage, the sun's shining directly into your camera. There's nothing you can do if all you're seeing is white, right? So it doesn't matter what algorithm you have. So that's a example of vision works where it fails, right? And then there are lots of systems aspects of it, how you do maps, how you do simulation, how you have to do testing. So that's what the simulation part of it, and motion planning, right? So the bad part is you have to spend a lot of time getting autonomy, right? And then comes the ugly part, right? The ugly part is really that generalization is something that we still don't know how to attack it, right? So there's a question about whether we should have the best simulator or whether we should actually work with worse simulators to do this, right? There's a question about whether it makes sense to have very good maps and then kind of work on those maps, or whether it should be something where you don't have any maps and you kind of do things using fairly by understanding what's happening in the environment, right? So these are questions that are active topics, and there's no good answer right now because we've just started asking those questions. Okay, so I will stop there, and I'm happy to take any questions.
Thank you so much, Srikanth, for a very insightful talk. I have one question. Do you deploy continual learning in your system? And if yes, how challenging is the scenario in an on-road autonomous vehicle scenario?
So yes, we haven't done any continual learning on the shuttles, but we have well, on the off-road vehicles, our perception modules are learning on the fly, right? So because most of these they're trained on some data set, and they are looking at different things. So something that you see in Texas is completely different than what you'd see in Michigan to what you'd see in California. So you definitely want to do that. We have not done end-to-end, and there are a lot of people who do field robotics, and it's not clear to us that end-to-end learning is the way to go. Again, that's because the systems engineering aspect of it kind of comes into the picture, right? So a lot of the end-to-end learning systems that you see right now are for manipulation. So you want to pick something. So if you see the latest papers from Google or Meta or anything, they're all for manipulation. There are very few end-to-end learning systems that are actually for mobile robotics. Tesla hopes to get one going. That's what they announced, but it's still up in the air as to where they are. There are some startups that claim that they are doing end-to-end, but you have to understand that anybody can create a good video on a particular day, right? So it's the question of, can I actually run it hundreds of miles or thousands of miles and things like that. So most of these videos, when you see them, they're cool. They're very good research papers. But in real life situations, I would take them with a little bit of salt, because they are one instance of the system working, not like you haven't shown anything that says that the system works over a significant period of time, or it will work when you see something that you haven't seen.
There's some questions online.
Hello.
Yes. Hey.
Hi. Yeah, I had a quick question. This is regarding the mixed domain interactions where you do the simulation and the reality. Are these agents trained on the interactions in the simulation? And if so, are there any cross-domain adaptation methods needed for the transition to be effective in the real-world environment?
I think that's a really good question. There's recently a DARPA call that was exactly looking at it that came out like last week, no, 2 weeks back, called I don't remember the full form. It's called TIAMAT, TIAMAT. So for the first answer, yes. So we are training these interactions in simulation, particularly because you cannot have a real life collision, money. So you don't want to do that. And the second question, there are several methods. The jury is out there, which one actually really works. Everybody has their favorite method, or let's say that this is a completely open topic where you will see a paper out every week saying that our method's better than the previous method. But I think consider that as actually a very good thing because there are several people who are interested in it, right? So there's the other question of, do you even really need the kind of simulations that I was showing you? Why not just do it in like I mean, the favorite thing is say Minecraft or something like that. No, I mean, right? So humans understand, like if I hit something in Minecraft and that's bad, so kids, at least my kids, they play a lot of Minecraft, but they can relate to something that happens in a video game and take it and kind of relate to that in real life, right? So can we actually do that is a very interesting question. Do we have methods to do that? I think people are trying, but that's a very active area of research right now.
Thank you so much.
Thanks.
Thank you, Dr. Saripalli. I have a quick question. This is Panos Markopoulos.
Yes.
I want to ask you, so you talked about the terrestrial vehicles in also in off-road settings. And I was thinking, if there is research in the synergy between terrestrial and aerial vehicles, with the aerial vehicles giving some kind of a look ahead images so that the terrestrial vehicles, and also they give a different angle than what the terrestrial vehicle can see. And maybe they could detect negative obstacles or potholes and things like that.
Yes, definitely. So there is a big push by the Army Research Labs and the Army Futures Command in that area. So air-ground cooperation, everything from what you have just said to questions about how you integrate that with people. I know there are teams that are already funded in this area, but expect call of proposals, things like that coming out from Army Futures, Army Research Labs, and ARL has something called Essential Research Programs, ERPs. So they think of them as 5-year programs where ARL has already committed money to do these things. And a big part of that is exactly what you have said. Of course, aerial vehicles. And then there are questions about aerial vehicles don't have enough energy. So when do they land? And do you want these to be tethered versus untethered? So you can think of any two axes, and all of these are very, very interesting questions that definitely the Army is interested in, right? Yes. So thanks. So the question that I have on the chat is, do you see deep reinforcement learning and AI vision algorithms completely eliminating traditional methods to control systems like PID controllers? I would love to see that, right? This is me being an optimist, but let me tell you the realist part of it. And this is maybe a little bit sarcastic. A PID controller pretty much works anywhere in the world. You write a PID controller, given an environment, it works anywhere in the world. A deep RL algorithm, once you take it from San Antonio to College Station, I'm sure you will have to retrain it. So the optimist in me wants to believe this, and hopefully somebody will do it. But I think PID controllers are amazing, and they're amazing because they're so simple and everybody understands them, and we know where they work and where they don't work. Deep RL is way too complicated. But like I said, I hope they go there. Yes.
Yes, I have a question. So,
yeah.
Thanks for the talk. So you were saying about like environments, the simulation environments where we train our models to be simple. But shouldn't they ideally be much more closer to realism? Like, shouldn't we build like much realistic environments to prepare the models, or have that easier translation from my simulation to real world, and prepare the models to be.
So the question, yeah, so I think that's a valid question. So if you know your operating conditions, then obviously you want the best simulation, right? So think about Boeing. When they build their, say, I don't know, 737, 747s, right? They are okay writing very traditional controllers, not PID, but very traditional controllers, let's say LQRs or H infinities, because they have the time, the space, and the energy to figure out what exactly their operational conditions are and when they can work and things like that to build that, right? But now think about like a lab that I have, where I don't have the energy or the money or the time to do that, right? So then I start thinking about black box methods and methods where I don't understand a lot about the dynamics of the environment and I want algorithms to work, right? I think it boils down to, do you understand your environment? Do you understand your edge cases enough? And if you do, of course, you want to build the best simulation possible. If you don't understand them, or if you're going to put them in places where bad things are going to happen, maybe you want to kind of think about robustness by testing them in very simple simulations and seeing how well they actually work and how well they can transfer to real life. Yes, so skepticism around AI, I think it's a new field. I mean, AI is an old field, so let me clarify that. AI is a very, very old field. Deep learning is a fairly new field, so the skepticism, I think, is fairly valid. Um, and it doesn't help that every day there's some random person saying things. So I think as academia, we need to be careful about what we say and what we don't say, right? But I think AI still, or again, deep learning algorithms still need to show that they can work in real life situations. So it's on all of us to kind of show that before. I think defense is just like space, is one of those industries where adaptation and acceptance is going to take a lot of time. It's not like they don't put money. I know for a fact Boeing's putting a lot of money into AI. The DoD is putting a lot of money into AI. It's just that they don't see it being used in the next 5 years or 3 years. They are looking 20 years down the line and what happens then.
So Srikanth, in your lessons learned one, it was very interesting that you said to use lots of sensors on the device or on the vehicle. Usually we want to do it the other way. We want to use fewer sensors, right, for cost and several other reasons. And the fusion of the data from all these sensors, there's just a lot of burden, computational burden, size burden, and all of that. Maybe in some cases, don't care about the size. So it seems very against what I thought about autonomous vehicles. So can you comment a little bit on that?
Yes, definitely. I think it boils down to whether it's well, there are several axes in which you can think about that question, right? So if you are a company, with the exception of Tesla, so let's leave Tesla on the side for a second. I think you're worried about safety, or you're worried about bad publicity. Let me put it that way. I think then you understand that the sensors by itself have limitations, right? So vision cameras have limitations, dynamic range, signal to noise ratio. So the fundamental limitations of cameras kind of get in the middle of what you can do. So adding more sensors when you actually test is correct. By the time you've developed your algorithms, then you want to start removing those sensors, because then it becomes a cost versus, it becomes a cost issue from a company. From a research perspective, I think you're absolutely right, because you want to kind of push on the limits of what can be done from research. And so you can then say, well, what can I do just with just a vision sensor? Or you can even say, what can I do with the simplest vision sensor, right? So, and how far can I push that to with the simplest vision sensor, or with the simplest, I don't know, even with the simplest, say, a single line LiDAR or things like that before I add another sensor, right? So I think it just depends on how you look at it, right? So if you're trying to do a field robotics experiment, it depends on what your goals are. Is it sensor fusion? Is it an experiment where you want to show how good the system works? Which is one of the things, I don't know if I put it in here or not. So the last one, motion planning cannot be done in isolation, localization, mapping feed into it. I think kind of says that if you want to develop an entire system, these things all feed together. So one thing that sometimes doesn't work kind of makes the other things not work.
I think you need lifelong learning models for these autonomous vehicles, is what I think. There's a
So
opportunity there.
Absolutely. So about 5 years back, well, not 5, maybe 7, 8 years back, there was a big push on lifelong learning, but more traditional learning, right? For autonomy. And now we have come full circle for where people are talking about lifelong learning. So they've just started calling them world models instead of lifelong learning models, but that's what they are. So there's a company called Wave, WAYVE, which is British, and they're pushing them quite a bit for autonomous vehicles. And yes, so if you need models that change, you need models that adapt, you need models that can look at all these things. Yes, absolutely.
Thank you so much, Srikanth, for taking time to share this research of yours. Seems like very fun projects to be outdoors and exploring the wilderness through your research.
Thank you. Thanks for inviting me. I'm sorry I couldn't be there, but definitely next time, hopefully next time, I'll be able to visit UT San Antonio. Thank you. Thanks a lot.
Thank you.
Thanks. Thanks. Bye.